This problem is very similar to the previous problem, except now you're giving it a little push. So in the previous problem, you just had a displacement of -1, or sorry, zero point 0.1 meter, and then you released it from rest. So you know that was going to be the largest amplitude it can ever be. Now you're giving it a little push. So that extra kinetic energy means that it's going to go from that negative zero point 0.1 meter to positive zero point 0.1 meter and a little further because of that extra energy. So you know that x naught is no longer an amplitude. It's going to be, the amplitude is going to be a little bit bigger than zero point 0.1. We're going to go ahead and take that omega being 8.08 radians per second from the previous problem as stated in this new problem. And for part A, which is the whole point of this video really, is to find phi, because that's the hard part. So let's go ahead and do that. First thing is let's look at equations of state. So you got the position equation, you got the velocity equation. Now, this is not too helpful because what they do give us is only the initial condition when t is equal to 0. That's kind of perfect because when t equals 0, the first term cancels or goes away, leaving only the phi, which is eventually what we want to find. So let's go ahead and mark out the initial condition equation where t is equal to 0. Now that omega t is 0, cosine of phi is what's left. For v naught, we have the same thing. Omega t is 0, so phi is what's left. Well, that's perfect. We have, or what we need to find is phi for one of these two equations. We know what x naught is given in the problem. We know what v naught is, and we know what omega is. The issue is we don't know what a is, but we can come up with something clever. Why don't we say tangent of theta, or sorry, phi, is equal to sine of phi over cosine of phi. Now what we can do is we can take sine of phi, isolate it in terms of v naught, take cosine of phi and isolate that in terms of x naught, and take the ratio of the two to get a tangent phi, which would then give us what we want to find eventually. That's going to come out to be negative v naught over omega a divided by x naught over a. Simplifying a little bit, we get this. And voila, we see that the common form here from the numerator to the denominator is a, which we can then cancel out. And that's perfect because that's the thing we didn't know. So that's just being a little clever. So now we have tangent of phi equaling to negative v naught over omega x naught. Now, if you plug all those values that you got from the initial knowns of the equation into this, we get 0.495 and it's unitless. Okay, so now the next part is to just find phi. And you do that by taking an inverse tangent of this number. This is where it gets a little difficult, so you need to make sure you pay attention here. The calculator is going to spew out one value only. But as we learn in trigonometry, there's actually going to be two values. I'll show you how this comes about. So look at the unit circle, for example. You see that the first value comes from this first quadrant. So 0.46 radians is between 0 degrees and 90 degrees, or pi over 2. So this is 0.46 radians, first quadrant. And it makes sense because we know that sine and cosine are both positive. Sine is associated with the y-axis. Cosine is associated with the x-axis. They're both positive, so the tangent should lie in the first quadrant. So the question is, how else can you make tangent a positive? Well, the ratios have to be both positive, or the ratios have to be both negative. And that comes about in the third quadrant. So both of these quadrants, in terms of whatever phi has to be, are both solutions to the tangent function. Here's the trick. You take the first function, you add pi, and then you get the second function. And as you can see, this is just going to be 3.14 plus 0.46. That's going to be about roughly 3.6 radians. Okay. So from that, you will get your second solution. And whatever falls within 2 pi of radians is all the solutions you need. So the next solution will be up here again, and then down here, and then up here, and then down there. So you only need 2 solutions. Okay, now the last part is how to find out which solution is correct, because they both can't be correct. Well, you do that by looking at the problem at hand. So you see that the oscillator initially starts off in a negative place. So it's a uh, negative location with respect to a reference frame, but it's going in the positive. This x function is a cosine function, so that means that this oscillator is simulated by the x-axis of the unit circle. If you start in the negative, you start off in the third quadrant or the second quadrant. We obviously know that the third quadrant has to be the case though. But we can further say that because not only does it start in the negative, but it's going in the positive direction. Now, when a trigonometric function simulates an oscillator, it goes in this sort of counterclockwise fashion. So a unit circle is going to go like this for each oscillation. And we're only looking at the x-axis when we look at an oscillator. Well, when something is here, when the unit circle is right here in the third quadrant, it's in the negative x component. It has a negative x component, but it's also going this way because it's finishing off its counterclockwise orbit around the center. So not only does this phi simulate a negative x value in the x axis, but it also simulates a positive going motion. So the third quadrant definitely has to be the phi that we're looking for, negative and positive seeking. So the answer is going to be 3.6 radians, and that's going to be our answer for phi. Now let's go ahead and look at B and C, which should not be as difficult. So for B, we want to know what A is. There's many ways of doing it, but I think the easiest way is by just using the initial condition equation again and then finding A properly. Let's go ahead and use x naught since that's easier. It's equal to A cosine of phi. Now we know what phi is. It's 3.6 radians. And we know what x naught is. It's negative 0.100 meters. So A comes out to be 0.112 meters. Not only that, but if you want, you can verify by using the V naught equation. You can plug in phi, phi, omega, and V naught, and you can find A to verify that A has to be 0.112 meters. Now for part C, all you're going to do is just put what we found out into one universal equation. So the general displacement equation as written right here is A cosine omega t plus phi. Plugging in the phi that we found out, the omega that's in the problem, and the A we found out for part B, we get x of t is 0.112 meters cosine of 8.08 radians per second t plus 3.6 radians. And that's our final answer. Here's the top of the page with the initial conditions. And here is including all of the other parts of the work.